Let's take a look at another example here. Let's say f of x, instead of having this just be rational functions, I'm going to modify just a little bit. So now we're going to talk about f of x equals, I'm going to throw a square root in here. So square root of 1 plus 4x to the sixth. And this is divided by 2 minus x to the third. Okay. All right, so we could think about what's the largest degree here. Now, it looks like there's an x to the sixth, but when you think about the square root there, it's not okay for you to just take the square root of 1 and the square root of 4x to the sixth separately on the top. That's not allowed. But if you were to think about kind of dealing with a square root of a 4x to the sixth, that would be a third degree. So even though there's that 1 on the top that's kind of messing things up, really the top is kind of a third degree there as well as the largest degree. So you could actually do the same thing here. If you're talking about what's the limit as x goes to infinity of this thing, of the square root of 1 plus 4x to the sixth over 2 minus x to the third, you could go ahead and multiply by 1 over x to the third divided by 1 over x to the third, just like we did in the last problem. Okay, look at what's going to happen here, and you can actually rewrite 1 over x to the third on the top. If you want to rewrite it so that it goes inside of the square root, another way to rewrite this is the square root of 1 over x to the sixth. Now you can bring that into the square root and multiply and see what happens there. So this is the limit as x goes to infinity of the square root of, if you bring that square root of 1/6 inside, it becomes 1 over x to the sixth plus 4x to the sixth. I'll go ahead and write this out, even though we know some things are going to cancel here. 4x to the sixth over x to the sixth. There's that top, and then the bottom, the 2 minus x to the third, just multiplies by 1 over x to the third. You get a 2 over x to the third, and then minus, well, you have an x to the third divided by an x to the third, so just minus 1. Okay, and then as we know, the x to the sixth and the x to the sixth inside there are going to cancel as well. So we actually have the limit as x goes to infinity of the square root of 1 over x to the sixth plus 4 all over 2 over x to the third minus 1. Okay, so same idea as before. Think about what happens if you were to plug in infinity, whatever that means, but plug in a really large number. Remember, back when we talked about limit laws, remember limits can move inside of square roots, they can move inside of fractions, they can kind of move to the place wherever there is an x involved. So when you take the limit of 1 over x to the sixth, remember it's the limit as x is going to infinity, that ends up being just 0. And then 2 over x to the third on the bottom, as x goes to infinity, that ends up being just 0. And what you're left with is the square root of 4 divided by negative 1. And so square root of 4 is 2. You end up getting negative 2 as your answer there. Okay, and again, this is just talking about the end behavior, saying what is your function approaching, what are the y values approaching as x is getting larger and larger and larger and larger as x goes to infinity here. Okay, by the way, this is why you also can't deal with this when if it were to say something like x goes to 2, this is not a very helpful approach, because as x goes to 2, now inside of the square root, you can't just say the 1 over x to the sixth goes away. It doesn't. 1 over infinity is 0, but if you only had x going to 2, that would end up being a 1 over 2 to the sixth inside there. That's not just 0. That's even a more complicated fraction that you've introduced now by trying to use this approach. So this only works when you have x going to infinity. Okay, so one last thing. We said earlier that along with rational functions and some other types of functions, exponential functions also have horizontal asymptotes. So I want you to think about what the graph of f of x equals e to the x looks like. You should have this graph in mind, and not just e, but if you had a base of 2 or 3 or any other base, it would look like this. And the idea is that there is a horizontal asymptote on the x-axis, but it's not as x goes to infinity, it's as x goes to negative infinity. Okay, so in other words, the limit as x goes to negative infinity of e to the x is equal to 0. And if you think about the graph of f of x equals e to the negative x, that actually is the graph that looks a lot like that, but it's a decreasing graph instead of an increasing graph. So another way to think about this is that the limit as x goes to infinity, positive infinity, of e to the negative x is also equal to 0. In other words, they both have a horizontal asymptote on the x-axis. It just depends on which function you're talking about. Are you talking about the increasing function of e to the x, or are you talking about the decreasing function of e to the negative x? Okay, so these are both good things to keep in mind, and keep in mind that the first one is talking about x going to negative infinity. The second one with the decreasing function is talking about x going to positive infinity. To save yourself some hassle, I would just recommend when you have a function, just think about the graph of that function, and then what happens when you go really far to the right, or what happens when you go really far to the left, and thinking about horizontal asymptotes in that way. So I'd rather you think about the graph and kind of approach it by understanding what's happening as x is getting really, really large or far negative, rather than trying to just memorize some formulas of this limit of this function is equal to 0. So I wouldn't try to memorize these, just visualize the graph and go from there. So let's go ahead and take a look at one last example that involves an exponential function that's kind of similar to what we saw before. Let's say we have f of x equals 1 minus e to the x divided by 1 plus 2e to the x. And we could go ahead and find the limit as x goes to infinity. So it's important to keep in mind whether x is going to infinity or negative infinity of this function. So something like this right here. And you might ask a question like, could we do the same thing we did before? Could we try to multiply by a fraction on top and on bottom that kind of gets rid of something? Now, that wouldn't be a largest degree here because this isn't a polynomial on top and a polynomial on the bottom. But we can actually do something really similar to this. And by the way, there's more than one approach to this. I'm just kind of showing you one approach. But I like this approach, and I think this is what our book uses. This is what is really commonly used. So let's multiply by a fraction, but instead of it being the largest degree on the bottom, now it's going to be 1 over e to the x. And over on the bottom, it's going to be 1 over e to the x. So look at what happens if you simplify this. This is the limit as x goes to infinity. When you multiply 1 over e to the x by both of the terms on top, you get 1 over e to the x, which, by the way, another way to write that, 1 over e to the x, another way to write that is just write it as e to the negative x. One of the best, this is just a side note, but I think one of the best things that you can do as we move forward in this calculus course to prepare yourself, especially as far as background algebra skills go, is to make sure that you know and know really well how to convert fractions into exponents and using negative exponent properties. So that's one of the best things you can do. So let's go back to the problem. We have 1 over e to the x minus, let's see, e to the x divided by e to the x. That's just a 1. And then on the bottom, we're going to have 1 over e to the x also. And then, let's see, plus 2, because you're going to have an e to the x on top and bottom. Now, if you think about a graph, again, don't memorize limits, but if you think about a graph, 1 over e to the x is another way to write that is to write it as e to the negative x. I guess we don't need a graph here. And so you can rewrite this as the limit as x goes to infinity of e to the negative x minus 1 over e to the negative x plus 2. Now, no, the e to the negative x's do not cancel on top and bottom. That's a common mistake I see from students. But if we look back on the last problem, the last page, what we would see is that as x goes to infinity, e to the negative x just becomes 0. Those just go away. And that's the example of this decreasing function right here, and saying as x is going to infinity, that function is getting really close to that x-axis. So what do we get for the limit? We just get negative 1/2. Okay, so I think that's about it for today as far as horizontal asymptotes. I hope you've enjoyed, and good luck practicing.